Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 19th, 2026, just 6 days ago. It introduces a dynamic tokenization strategy that achieves up to a 3.5 times speedup on models like Flux 1 Dev and WAN 2.1, all without compromising generation quality. The paper is titled DDiT, Dynamic Patch Scheduling for Efficient Diffusion Transformers. And as we'll see later, the results suggest a promising shift away from fixed compute budgets for generative AI. Figure 1 demonstrates its performance across modalities, with text-to-image results on the left and text-to-video on the right. The top row establishes the high-quality baseline using standard models like Flux 1 Dev and WAN 2.1. As we move down the panels, DDiT accelerates generation, reaching roughly 3.5 times speedup for images and 3.2 times for video at the bottom. Crucially, even at these high speeds, the visual output remains virtually indistinguishable from the slower original models. Well, Figure 2 illustrates the core mechanism behind this efficiency. The top row shows a standard diffusion transformer applying a fixed, fine-grained grid for every step, which keeps the computational cost high throughout. In contrast, the bottom row demonstrates the DDiT approach. It starts with very large, coarse patches at early time steps, when the image is mostly noise, drastically lowering the cost. Then, as structure emerges around time step 400, it dynamically switches to finer patches, effectively spending compute only where it is actually needed. So, Figure 3 details the architectural changes, enabling this dynamic resizing. The top panel shows the standard approach, where the embedding layer is locked to a fixed size P, forcing expensive processing regardless of content. Panel B presents the DDiT solution, which adapts the embedding layer for variable sizes, labeled P-new. Crucially, the base model remains frozen, marked by the snowflake, while a lightweight low-rank adaptation branch, or LoRa, is added to handle the new scales. This design allows the system to process coarser patches efficiently, dropping the cost gauge into the green without retraining the whole network. Alright, Figure 3 explained the how, and now Table 1 shows the result. It compares DDiT against top competitors like Tcache and Taylor Sear. The rows are grouped by speed, blue for 6-second runs, and yellow for 3.5-second runs. In the blue group, DDiT achieves the best FID score of 33.42. And in the yellow group, combining DDiT with Tcache reaches the fastest speed of 3.4 seconds, achieving the massive 3.5 times speedup mentioned earlier. Moving from the metrics to the actual visuals, Figure 7 compares the generation quality across these methods. The first column sets the standard with the original baseline model. In the middle columns, competitors like Tcache and Taylor Sear achieve about a 2 times speedup, but if you look closely at the zoomed-in patches, like the dog's eye or the elephant's trunk, you can see artifacts or color shifts. In contrast, the rightmost column shows that DDiT maintains sharp, accurate details at the same high speed, virtually indistinguishable from the slower baseline. Well, having verified the visual quality, let's look at the mechanics. Table 3, at the top, optimizes the complexity estimation. It finds that a third-order difference equation, n equals 3, best captures the temporal dynamics, yielding the highest scores. Figure 10, below, illustrates this adaptivity in practice. The plot tracks patch size decisions over time for the sample images. Notice the blue line for the zebras. It drops to fine patches early. In contrast, the green line for the simple apple stays coarse much longer, efficiently saving compute. So, wrapping up, the big takeaway is that treating every generation step equally is a waste of resources. By dynamically adjusting patch sizes, DDiT delivers a massive speed boost over 3 times faster without retraining the base model or sacrificing quality. This points toward a future where compute is allocated intelligently based on content complexity. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.